Okay, while people are settling in, I'll just start with some reminders. So, welcome to this session. This is the Active Galactic Nuclear Science session at the Rubin Community Workshop 2025. So we have.
Whoops.
Hello. Oh, that was you. Okay. So this is a fully, I guess the presenters are fully virtual, and I am the worst person with Zoom. So, but we have seen these reminders a few times. Please follow the code of conduct. Be respectful of people's, I guess, zone of comfort, both health-wise and also socially. But yeah, so like I said, this is a fully, all of the presenters are virtual. So all the virtual participants should stay muted when they're not speaking. So we do have a Slack channel. You can find it as day 2, Tuesday, 1:30 AGN session or something like that. But since all of the presenters should share their screen in order to present, and yeah, we have someone who will be keeping an eye on the Zoom chat, who will raise their hand in order to signal that there's a question in the chat. But I'll also be taking questions in person, and I will try to announce when you have 2 minutes left. But now we'll stop sharing. Okay. And so first up, we have Sarath Satish Shiva, who will talk about constraining the photometric redshifts of quasars using variability in the LSST era. And are you there?
Sure. Yeah, hello. Can you hear me?
Yes. Yes.
Okay, excellent. So, so I hope you can actually see my screen as well. Can you confirm if you can see my screen?
Yes, I can see.
Okay, excellent. So, should I start?
Yes, whenever you're ready.
Okay, all right. So, hello all. I guess it's good afternoon there, and thank you very much for giving me the opportunity. And for the people who doesn't know me, I'm Sharath Satish, and I'm a final year PhD candidate at the Universidad Andrés Bello in Santiago de Chile. And this is my primary thesis topic, where we are creating a tool that can be used to constrain the photometric redshifts of quasars using variability, and I call this tool VARPC. And this work is being done in collaboration with Roberto SF as my supervisor and Timo Angita as my co-supervisor, along with the LSST AGN Science collaboration. And moving forward, so as we all know that the AGN are variable sources, and we have different models to study the AGN variability, and one of the most commonly used model to statistically explain the AGN variability is the damped random walk model, where the damped random walk model can be used to study the amplitude of variability and the damping time scale, as well as the asymptotic amplitude of variability. So on the right side, you can actually see a structure function of a quasar, and this is something which we use to study the stochastic variability of AGN as a damped random walk. And I'm not explaining much more about the damped random walk considering the time. So in the Rubin era, we knew that the LSST is going to discover tens of millions of new AGNs. But as we know that selection of these AGNs, as well as the photometric redshift estimation of this AGN, has always been an active research problem, particularly because of their smooth continuum in the SED. And you can actually see an AGN SED with the slow and photometric bands on the right side. And you can see that the SED is quite smooth with very less features. Our sources are variable, and at low redshift, there can be higher contamination from the host galaxy and factors such as obscuration. And These factors indeed affect the estimation of the photometric redshifts of typical AGN using traditional SED fitting methods, and this can really cause degeneracies. So through our tool, we are actually trying to overcome these degeneracies and helping any other models such as SED modeling or any other machine learning models to choose the to overcome the degeneracies and choose the right photometric redshift. So I'll before going to how my algorithm works, I will explain a bit about the data which I'm using here. So I'm using SDSS type 82 quasars, where the parent sample includes 9,210 sources within the redshift range from 0.3 to 5. And I use all the 5 bands of Sloan, the photometry, the light curves, as well as I simulate light curves to see how things will work in the LSST era. And giving a quick introduction on the this tool, the VAR PC tool. So as I mentioned, I modeled the AGN variability as a damped random walk, and this is actually the empirical model that was suggested by McLeod et al. In 2010, where she tries to relate the asymptotic variability as well as the damping timescale of the variability as a function of the rest frame wavelength and the absolute I-band magnitudes, as well as the black hole mass indeed. So since for most of the objects, we will not have black hole mass, at least in the near future, I'm actually removing the dependency on the black hole mass for modeling, but I do use the black hole mass for simulating light curves, which I will explain it later. So how are we relating to the redshift indeed? So the bottom figure actually shows the distribution of the correlation of the two variability parameters, the damping timescale as well as the asymptotic variability as a function of function of the rest frame wavelength, which indeed is the redshift. And we followed the same method that was used in that paper of MacLeod, and we actually estimate these coefficients A, B, C, and D through my method as well as in comparison with the MacLeod method. So if you see that these values are slightly different, particularly because of the absolute I-band magnitude, where I'm using my own SED modeling algorithm or using the templates, using the low resolution templates of Asaf et al. 2010, as well as through a different light curve modeling algorithm as well. So, but in principle, the way this routine works, I can actually give uh, a an important the routine. So this is the total routine of this WarPC tool. But considering the time, the important thing to keep in mind is that it actually accepts the photometric data as well as the light curves input, and then it fits the photometric data through the SED and for as a function of redshift, and for each redshift it tries, I actually get an AGN fraction. That's the AGN AGN host flux fraction, as well as the absolute I-band magnitudes. And then I use these two parameters in the damped random walk model that was designed by MacLeod. But in principle, we have all actually created a custom damped random walk model that is able to simultaneously fit these two parameters, the damping timescale as well as the asymptotic variability together as a function of redshift. And then this kernel is being modeled through a Gaussian process. And here we use Celerate to model these light curves as a function of redshift by fitting these two variability parameters together, and then we actually obtain the likelihood of that particular redshift. So and this is being done without the use of MCMC currently by running it through a grid of redshift from 0.3 to 5, but in principle we can actually use MCMC as well, but it will make the modeling a bit slower. So, and as I mentioned, I applied it to the real
You're out of time.
SDSS sources. Sorry.
You could wrap up since we are out of time.
Okay. Is it fine or? Okay. So I heard some noise. So as I mentioned, I applied this to the real data of the SDSS light curves. And towards the left, you can actually see the probability distribution function by that is given by just by fitting SED as well as by modeling the variability as well. And you can actually see the combined posterior that is helping to predict the photometric redshift very accurate in compared to the spectroscopic redshift. But the SDSS real data, so the even though the SDSS light course spans for almost 11 years, we found that only the last three seasons of the SDSS light course, spanning about 800 days, is giving really good variability information. I mean, they have the dense sampling enough to model the variability and to rely on those variability parameters. So hence we limited our sample, the light course, by choosing only these small regime where we have good denser light course. And this in fact brings us to the limitation that we will not be able to probe higher redshift sources because we just don't have enough baseline. And this comes from the theory that we need, I mean, the baseline that we use should at least be 3 times longer than the damping time scale. So in this figure, you can actually see the estimated time scales as a function of the each redshift bin, and you can actually see that, and this dashed line is the current SDSS baseline, which is about 800 days. And you can actually see that beyond 0.7 we really don't have any constraining power on the redshift. So we tuned the application of this model in such a way that the algorithm will not give its opinion about the redshift beyond the regime where it does not have a constraining power. So using this tuned mechanism, so the way it works is that it will predict the photometric redshift at the place where it has the constraining power, and above that it will just flatten the priors so that the whole constraining power goes into the SED or any other photo C algorithm that you are using to model. And the figure, you actually on the right, you see the SED, the spec C versus photo C of on the top is just used by using the SED modeling, and on the bottom it's by combining both SED as well as this tool. And you can actually see that it is able to remove a lot of outliers in the low photo C regime, so where the SEDs tend to have a degeneracy. But you also see that there are some clumsy of sources where variability is unable to remove. This is just because the variability, the light curves are not long enough, and so we just don't have enough constraining power to improve the redshift at redshift 2 and 3, etc. And the table, it's actually a comparison of the SED as well as the SED plus variability model to see how much it improves. And you can actually see that there is an improvement of about 11% in the outlier fraction just with this 800 days long light curve. And particularly if you move through low photo C regime, so where the SED peaks, SED says that the photo C is less than 0.6, where the variability has the constraining power, you can actually see an improvement in the outlier fraction by almost from 75%, the outlier fraction has decreased to 33%. And this is a significant improvement. And we have also compared it to the SED modeling from LEFR, which is a totally different SED model. And we also see an improvement in the by applying this variability model. So and then this limitation is only given by the real data, and hence we went on simulating this SDSS data. And this heat map actually shows the results, that's the outlier fraction, as well as the precision that we obtain by simulating a set of SDSS baselines and cadences. So an SDSS cadence is typically about 7 days, and a season is considered to be about 270 days, in fact. And as you can actually see, the best possible scenario where there is a 10 days, 10 seasons and a single day cadence, we have the best result. And the worst case scenario, we have the 1 season and 10-day cadence, we have where it's actually we have the same SED outlier fraction. And with the existing SDSS seasons, which is about 3 seasons and 7 day, we are actually receiving the similar improvement that we see in the real data as well. And this confirms that if we have a really good sample data, sample light core, we'll be able to improve the photometric redshifts of AGN at higher redshifts as well. And then we went on to check how it will
I'm so sorry,
improve in
Sarah.
the.
We are way over time. If we could ask you to stop sharing so we can go on to the next talk. I'm so sorry.
Oh, I'm sorry. Okay, okay. So, yeah, I can. So the conclusion is that we actually simulated the light curve for the LSST with both wide fast deep as well as deep drilling field cadences, and we find that with the LSST we'll be able to improve the redshifts of AGN predicted by any other model at higher redshifts as well. And I stop it here, and I'm sorry for overshooting the time, but feel free to contact me if you have any questions.
Yeah, thank you. Feel free to continue the conversation in on Slack. And we might have some time at the end anyway for questions. But Swayam, if you're ready, we have Swayam Panda talking about exploring the potential for active galactic nuclear emission line delays using Rubin LSST.
Thank you, Gloria. Can you all hear me over there?
I can hear you and I can see your screen.
Perfect. Thank you for the confirmation. Thank you for this opportunity. So sorry that couldn't be there in person. So today I'm just going to briefly summarize the things that we have been doing in the past couple of years, a part of Polish in-kind contribution, and also related to a bit from the Brazilian side, and now me personally being in Chile as a Gemini Science Fellow right next to Ruben, about to happen. So my name is Swayantrupta Panda. I'm currently also a co-chair leading with Sadat Satish and Rebecca McElroy, the AGN watch list group under the AGN Science Collaboration. So very happy to discuss with you all later over Slack if you have any questions about that. So the topic of the talk today is about going to be emission line, and also towards the end a bit about the continuum line delays that we're going to expect and how we are kind of working towards maintaining a pipeline in order to gain the success rate of these AGNs that are yet to be discovered. So briefly, some physics around this. So this all revolves around the central thematic of reverberation mapping. Effectively, what really says that we take a pair of light curves, one a proxy of the continuum, the other a proxy of the continuum plus emission line contamination. And when we do a cross correlation, we can recover the light travel time delay of these medium that are basically giving us these emission lines. Effectively, using that information, we have been able to now, at this point, done this reverberation mapping for more than 400 AGNs, where we have defined reverberation BLR sizes, at least in the local universe, as well as extending to higher redshifts using proxies such as magnesium-2, carbon-4, and other emission lines. So here we have a sort of a empirical relation that gets born out of this information, that is the standard radius luminosity relationship, which effectively at some point can be helpful as standardizing AGNs to become cosmological candles, effectively by using them along with other distance indicators and trying to bridge this gap between the local universe and the high redshift universe, and trying to be the bridge between the Hubble tension, so-called Hubble tension that we are sort of confounded with, using AGNs as an independent proxy, given that we are able to independently derive the luminosity distances for individual of cases of these AGNs. Also with the start of LSST, this is only going to get better. So as we say about Rubin, there's a lot of work that has been carried forward from the AGN Science Collaboration side. Sarat gave a very nice talk about the photo Z estimation. And one side of that is actually trying to involve the photometric filters and trying to predict sort of mock light curve performances that we are going to anticipate from the upcoming cadence surveys of LSST. So in doing that, we have been working quite tirelessly on the modeling of the agent variability, not only the emission lines, but also the continuums, as I said. And in this parameterization, we have been doing a lot of heavy lifting with real-time light curves from different observatories, spectroscopic monitoring, as well as combining them with photometric monitoring from existing surveys like ZTF. In this mock light production, we are kind of simplifying the approach here, trying to amplify the speed that we can really help us to generate the light curves. But not only that, but when the real data comes in, we are able to estimate their lags very efficiently in a very short period of time. So effectively summarizing this, at this point, we are able to ingest the different cadence simulations and with taking into account the photometric accuracies and distribution of black hole masses and spectral properties from existing surveys like SDSS and compounding these emission line contamination, which includes the emission lines themselves, the diffuse scattered emissions from the BLR, and host galaxy contaminations, along with iron contamination and these different sort of contaminants that add up to the information of the accretion disk, we are able to now develop these mock light curves using the approach of the Timur-Koenig algorithm and applying the power spectral densities that we have already been studying a lot on these HENs. Now, effectively, the code is able to create pairs of light curves, and then we are able to modify and improve on our modular approach of determining time lags using all the different various cross correlation and time lag recovery techniques. So just to give you an example, this is a representative light curve simulation from one of very old simulations from back in 2022. This is baseline version 3.4. Of course, we have been graduating to 4.3, and supposedly we are coming along to the point where the final cadence strategies are going to be established. So effectively, this is one such example of one of the deep drilling fields. And while we convolve this with our mock light curve recovery, we're able to provide a success rate mechanism of a range of redshift for which the Rubin observations are going to be taken care of. So effectively, when we are looking at this sort of setup, we are able to emphasize the different emission lines as a function of redshift and how across the length of the campaign, effectively the radius luminosity relations can be built up for all of these redshifts and luminosities taken together. Of course, we are trying to also establish the performance of different baseline studies, both DDF fields and the baselines, and including the TO opportunities that have been graduated in the version 4 simulations, and effectively trying to emphasize a metric of success rate in order to see in which kind of survey strategy we are able to efficiently recover the lags for BLRs as much as possible for the big sample of HENs. And effectively, we don't only stop on that because of the latest setups and the latest incorporation in the version 4 sims. We're trying to also find out salient differences in different deep drilling fields and the wide fast deep. I'm here concentrating on one of the deep drilling fields, the Elias S1. And effectively, what we have found that there is an overall success improvement for the version 4 simulation compared to the version 3s. Effectively, but the success rate underperforms when we are actually worrying about the redshift range between 1.7 and 2.5. This is exactly where the Lyman alpha enters the spectrum in the U band and magnesium 2 exits in the Y band. So that's a sort of concern. That's something that we are trying to also understand a little bit better. But in the end, the low Z, low luminosity range, and the high Z, high luminosity range are actually getting better in the lag recovery. And effectively talking about contamination, this is also where one needs to account for these information of contamination other than just the emission line, such as the diffuse continuum emission, in order to be able to reliably estimate continuum lags for HENs. And this has been a big effort from me and my colleague Francisco Pozo Nunes that we have been carrying forward over this analysis. And this is how we are able to also provide to the community a sort of a Gaussian process-based probabilistic cross-correlation technique that includes modular priors. And we take that as an example and try to test it for the recovery of continuum lags. Effectively, this is an example from the version 3.4 again for the continuum lags. And as you can see, the recovery is quite nice, especially for those high masses cases. But the problem for the small masses and the local redshift cases is that the sampling is not dense enough in order to give us reliable lags. And that requires much more denser cadence, like 1 to 2 days in all bands without significant gaps. And this is something that has actually got better with the version 4, effectively across masses and across redshift ranges, which is basically telling that the new baseline from the version 4 is actually really nice, and it's actually showing improvements for determining accretion disk time lag estimates. And this is basically trying to understand how the different complexity of this widespread variation of HENs can actually play a role, and how reliably are we able to estimate all these accretion disk time lags. And I'm going to stop here and take any questions if you have.
All right, cool, thank you. Does anyone in the room have questions for Swayam? No? Online? No? Okay. Okay. So next up, we have Ethan Parkington, who is going to talk about developing a supermassive black hole binary detection pipeline for LSST using null signal templates.
Hello, everyone. Thank you so much. Yeah, I'm going to be talking today about the significance testing method for searches for supermassive black hole binaries using a new null hypothesis method. And first, I'll discuss the prospects using LSST-like simulations, and then also transition into our results using the ZTF data release 23. So just as some background for what we expect from this kind of system, we expect in an accreting supermassive black hole binary at sub-parsec separations for there to be a circumbinary disk, and then as the black holes move in their orbits, the varying tidal forces due to eccentricity will cause them to shear off some of the circumbinary disk onto these mini disks. And that will be modulated by the orbital period, so or some factor of the orbital period. So these changes in mass accretion rate will correspond to a change in luminosity, and that will produce the periodic signal that we're looking for. Additionally, at very close separations, we could get Doppler boosting from the relativistic speeds that would also introduce periodicity. And the signal we're searching for is, of course, competing in our data with the quasar noise. So in large sky surveys like SDSS Stripe 82 and PTF, we see that this noise is very well characterized by a damped random walk with two parameters, the RMS variability, amplitude, sigma, and then tau, where on timescales shorter than tau, we have correlated red noise, and on timescales longer than tau, we get white noise. And this correlated red noise is really what gets tricky when we're searching for binaries. We have an underlying population of sigma and tau from the PTF data set that we are using to draw from in our simulations of LSST-like light curves. So these are produced with easy tau using a time sampling pattern developed by Eden Davies from Washington State University using the LSST operations simulator. And these are simulated for the R band in the wide fast deep survey. We produce 500,000 of these light curves and then inject a periodic signal in 0.1% of them. You can see an example light curve down here where purple is the injected signal, and then we have that damped random variability introducing additional behavior in the light curve. And to test for the significance of our recovery of this periodic signal, we are going to introduce a null signal template. So the null hypothesis here is that there is some underlying long-term variability, but that it is not a regular periodic signal. We use the null template in orange here and fit it over each light curve where it is a sinusoid with some mean period, and then each individual period is perturbed. So again, this is a null hypothesis. This would not be produced by orbital behavior in a binary. And we use the Bayes factor in our simulations as a test statistic. Later, we'll use the log likelihood ratio for computational efficiency with ZTF. But both of these statistics measure in the Bayes factor case, ratio of the evidences for a damped random walk plus this signal compared to the evidence for a damped random walk alone. And these Bayes factors produce a threshold above which we can consider a periodic signal detection to be significant. So this histogram here shows all of our 500,000 light curves. You can see the tail with the higher Bayes factors correspond to the 500 or so that had a periodic signal injected. And the yellow line, again, is the distribution of Bayes factors for the null signal template. So you can see that we get some very high Bayes factors for this non-periodic null hypothesis signal. And then we would consider any periodic signal templates with higher Bayes factors than this null baseline as significant. And with that cutoff, we get no false positives and a 20% true positive recovery rate. We do the same analysis with the same method, but using the real ZTF DR23 data as well, with about 600,000 total light curves that correspond to about 300,000 unique quasars due to duplication in the G and R bands. These are all spectroscopically confirmed quasars from SDSS DR16 and are above the limiting magnitudes for ZTF in each of the 3 bands. And performing this analysis, we get no smoking gun evidence for a black hole binary, a supermassive black hole binary, unfortunately. When we look at the distributions of the log likelihood ratios for the between the periodic and null signal templates, you see that the null templates end up producing slightly higher scores for the top of the distribution. And overall, the distributions are pretty comparable. So the periodicity that we're searching for is not strongly preferred over this null signal template in the data set. In the I band, you have this one quasar that slightly peaks out over the null distribution, but I'll remind you that the scores here are much lower than they are in either of the other 2 bands, and we don't see this behavior in multiple photometric bands. In the image on the right here, this figure is the I-band light curve that has the highest log likelihood ratio. And you can see above the same quasars G and R band light curves have much smaller log likelihood ratios that would not be close to the edge of the distribution. And then similarly, this on the left here is the highest R band log likelihood ratio. This is the highest log likelihood ratio of the whole sample. And again, there's no significant periodicity in either of the other bands, nothing even comparable to what we see in the R. And this persists over the top 20 highest scores, for instance. So all of those 20 highest scores come from 20 different quasars. There's no strong preference for a periodic signal across multiple bands. And this does unfortunately extend to the top 3 sources identified in the Chen et al. 2024 analysis of ZTF DR11. I have reproduced on the left here the figure from that paper, and then on the right is the updated through DR23 ZTF light curves shown in orange in Chen et al. And you can see that after DR11, there's a significant divergence from the signal that was kind of being picked up as periodic, and that these log likelihood ratios are pretty low in the overall sample. So in conclusion, the null signal template is an alternative hypothesis to the traditional assumption that the noise is periodic or it's a damped random walk alone. It provides a more noise agnostic idea that there might be some long-term variability that's not characterized by a damped random walk, and prevents us from mistaking that as periodic. It's also more computationally efficient than traditional methods because it doesn't require multiple simulations for each light curve. It recovers the injected sinusoidal periods well with the LSST-like simulations, and in ZTF, it rules out any possible periodic signals. And that's it. Thank you all.
Great. Thank you so much, Ethan. Are there any questions? Okay. So next up, we'll have Christian Wolf, who has shared a pre-recorded talk on the Australia-based AGN surveys and follow-up, and I will come up and play that. But Christian is on Zoom and available for questions after.
tell you about spectroscopic
There's an echo, right? They did say there would be a delay, but not a. Yes. But not here.
in Australia for AGN in particular. LSST is the most wonderful imaging survey. Imaging survey that has ever been attempted, but only spectroscopic surveys can tell you reliably what sort of objects you're looking at. So you can use existing spectroscopic resources to search for specific objects you want to monitor with LSST. Now, Australia has traditionally been very strong in the area of spectroscopic surveys. The 2DF facility at the 3.9 meter AAT telescope is famous for having observed more than 500,000 galaxy redshifts over the last 20 years. And presently, the ANU 2.3 meter telescope with the small IFU unit covering about half by half an arc minute and a spectral range from 350 to 950 nanometers simultaneously is also becoming a useful survey facility, even though it observes only one object at a time. For samples that are sparsely populated across the sky, such as the most luminous AGN, this is a very useful resource. 2DF, of course, was able to observe nearly 400 galaxies in a 2-degree wide field within one single exposure. So it was able to cover much larger numbers of galaxies and AGN in a short amount of time. But let's look at the data resources that have been assembled. Some surveys were specifically targeting QSO candidates as embedded in wider galaxy redshift surveys. This includes 2QZ and 6QZ that were part of 2DF-GRS and 6DF-GS. And AUSTES, the Australian Dark Energy Survey, was monitoring over 700 quasars for over 6 years in the DES supernova field specifically. Then we have 3 particular galaxy surveys that happen to contain AGN, low luminosity type 1 AGN as well as type 2 AGN. And these cover over 1,000 square degrees of southern sky down to about 20th magnitude. Devils goes deeper than that in a much smaller region though, and the data are only just about to be published. Let me start with a now 20-year-old hemispheric spectral atlas. Over 100,000 spectra of the brightest and most nearby southern galaxies were observed by 6DF-GS. And these include a number of type 1 and type 2 AGN. A catalog of about 2,500 type 1 AGN has recently been published by Hon et al. And a new catalog of a similar number of type 2 AGN is submitted and already on the archive. A smaller resource is the S7 survey, the Siding Spring Southern Seaford Spectroscopic Snapshot Survey, with only 130 objects at the moment being published. These were observed with the ANU 2.3 meter telescope with the WIFE's IFU. It's the most nearby AGN, not a complete list though. We have now extended this work of IFU spectral cubes for all of the over 600 Seaford 1 to 1.9 galaxies that we could find in the 6DF-GS at a redshift of less than 0.1 and south of the celestial equator. This will soon be published. In addition, we have been searching for very bright quasars, meaning mostly quasars brighter than 16th magnitude. These are nowadays very easy to identify by combining information from Gaia and WISE. The quasars, the stars, and the galaxies easily avoid each other in simple selection planes. And so it is very easy to create, these days, a catalog of bright quasars that is both 99% complete and 99% pure. We have thus compiled the AllBricks, the All-Sky Bright Complete Quasar Survey. Observations are going to finish later this year, and then the full sample will be published, but part of the sample is published already. It includes a few special objects, such as J1144 and J0529, which in their cosmic eras were the most luminous quasars found so far. This covers both the southern and the northern hemisphere, and with one of our recent publications, we have tackled the northern sky, and we have found new quasars, very bright quasars, even in the area previously observed by the Sloan Legacy Survey. In the future, we might extend this survey going a little bit fainter than 16th magnitude. Especially, we are concerned about filling the gap, the magnitude gap that we might leave with SDSS 5 or foremost, if those are not going as bright as 16th magnitude because of saturation issues, perhaps. Another quasar survey that we have carried out at the 2.3 meter is XQZ5. This was first a survey starting with Gaia WISE and SkyMapper, covering the entire southern hemisphere outside of the galactic plane. And we believe we have constructed a sample of quasars, which is flux limited down to a Z magnitude of almost 19, and which is complete in the redshift range 4.4 to 5.3. Our color selection criteria show a distribution of objects with tails inside of the criteria. So none of the criteria cut through the main distribution. This is why we believe the sample is essentially complete. And a fraction of these objects also has follow-up with the X-shooter instrument at the VLT. We've also been engaging in searching for quasars in the galactic plane at latitudes less than 20 and even less than 10. However, this search is highly incomplete at the moment. So, a quick summary. Very soon, bright AGN, brighter than 16th magnitude, will be known across the entire sky outside of a galactic latitude of 10 degrees and will essentially have a complete Type 1 catalog across all redshifts. Southern AGN at low redshifts less than 0.1 will be Type 1 complete very soon again with a full spectral atlas. Medium bright AGN, we have complete samples at redshifts larger than 4. And in between these various cuts, there are resources for AGN spectra, but they do not cover the complete parameter space yet. Thank you very much.
Any questions for Christian? Okay. Next up, we have Zachary Stein.
You can come through, okay? Take that as a yes. Okay, right, yeah. My name is Zach, and I'm a PhD student at the Australian National University. I'm going to chat a bit today about the work that I've been doing with my supervisors, Chris Wolf and Chris Onken, on continuum reverberation mapping. So to start off, what is continuum reverberation mapping? So in this picture, we have a central variable X-ray corona that shines on the surrounding accretion disk. This disk absorbs and re-emits that light with a slight light travel time delay. since the inner disk is hotter than the outer disk, we expect this response to be seen first at low wavelengths. If we have light curves in at least 2 bands, we can then estimate the size of the disk from the time delay between them. This has been applied in lots of different intensively studied CFIT galaxies, finding many robust lags. But these lags are almost universally larger than expected, in general by about a factor 3. So there's been many models in the literature that have been proposed to explain this phenomenon, including the diffuse emission in the broadline region, responding to changes in the continuum flux. And because this broadline region may to the larger radius and contributes to the continuum band filters, it essentially elongates the lags that we see. It's also been proposed that there's magnetic connections between the corona and the accretion disk. And then we thus overestimate the size of the disks by assuming the speed of light travel time rather than the alpha and velocity. Disk winds can drive radially dependent mass accretion rates, meaning that a greater fraction of the responding emission comes from the outer disk. Larger than expected corona heights is another way to recover this size discrepancy, as well as exploring disk geometries with ripples or steep rims at the inner edge of the BLR. Internal rendering from host galaxy dust also may cause us to systematically underestimate the luminosity of these systems and thus their expected size. Survey-based continuum reverberation studies have found that this size discrepancy decreases with higher luminosity. I know I've committed a little bit of a faux pas here and by putting quite a bit of text in this slide, but it's kind of to illustrate that there's a lot of moving parts in AGN, and they may have an influence on the lags that we measure. So we wanted to cut through all this and focus on a single phenomenon, and that is that size mismatch being anti-correlated with luminosity. So to explore this, we look at 10,000 of the brightest quasars in the sky, using data from the NASA Atlas system. This data contains light curves with a median cadence of 1 to 2 days, spanning an 8-year baseline, taking observations in 2 filters, cyan and orange. As you can see from the plot on the right, our sample extends to more luminous quasars, as well as more distant ones than previous comparable survey-based continuum RM studies. You might also note there's a strong correlation between redshift and luminosity, as is expected in a flux-limited sample. We choose to bring this sample in units of rest frame wavelength and log luminosity, which brings me into the next slide, stacking to improve the lag detection. So we're all aware of the benefits of stacking, in that you increase the amount of signal that you have while also marginalizing over properties that you can't properly constrain. So for about 20% of the candidate light curves in survey-based studies, can you get a robust lag measurement? We wanted to see if the rest of that data that can't really constrain a lag measurement on its own can still be useful. And we do this by stacking at the inference level. But what do I actually mean by that? So for the popular reverberation code ICCF, this means combining the cross-correlation functions that are estimated for each individual object, essentially treating them as independent realizations of the same class. And it's then from this combined cross-correlation function that we get the lag measurement as the centroid. Similarly, for another popular code, Javelin, which takes a Bayesian approach, we simply sum the likelihoods through the bin. We kind of already, in a sense, are doing this by applying these reverberation codes to entire light curves, because in some AGN, it's been shown that the lag behavior is time varying. We compare the application of this method on a simulated dataset that's been calibrated to the real Atlas data, finding that when we apply these codes to individual light curve pairs, we can't really constrain the underlying lag distribution. When we apply basic quality cuts based on significance and lag uncertainty, we preferentially select longer lags and bias our recovered distribution. When we combine posterior samples of these lags, we alleviate this bias, but we can only really constrain the lags on the longest scales. Finally, when we use the stacked methodology, we really increase our ability to constrain this underlying time delay distribution. When we apply the stacked methodology in the real Atlas data, we recover that anti-correlation between the observed and expected size with luminosity that's been previously seen. But noting that our luminosity is highly correlated to redshift and therefore rest frame wavelength, we want to try and control for these effects. When we do, looking first at the most red wavelengths available in our sample, we don't really see this size discrepancy going away. We see lag scaling as expected, but with a normalization that's about 3 times higher, which is that red line, which is consistent with those CFIC galaxy studies. As we move to shorter wavelengths and our filters straddle the Balmer jump, it becomes a bit more difficult to constrain these lags, and they show a bit more of a flat behavior. Going shorter still, when the Balmer jump heavily contaminates our response band, which is the orange filter, lags begin to scale as expected again with that higher normalization. When there's a prominent amount of UV ion emission in both the cyan and orange bands, we see that these lags kind of flatten out and almost become independent of luminosity. For our shortest wavelengths, again, scaling is expected, but with that normalization that's much more consistent with the standard accretion disk theory, which is that gray line. The fact that we have this complex wavelength dependence in our lag behavior points that there must be at least some level of diffuse contamination in these continuum band lags, as all the other models predict a much more monotonic relationship with wavelength. And it's this complex behavior that's really driving the anti-correlation that we saw on the previous slides. So to summarize, time delays between continuum band light curves can be used to measure linear sizes in AGN, and these time delays can be estimated more accurately by stacking at the inference level, rather than combining posterior samples of individual lags. When we try and measure these time delays in real AGN, we find that we have a complex dependence on rest frame wavelength, pointing to some level of contamination from the diffuse continuum. Thank you. Happy to take any questions.
Thank you, Zachary. Yep. Any questions? Okay. Next up, we have Maria Carisi, who's going to talk about searching for supermassive black hole binaries.
Hi, everyone. Can you see my screen all right and hopefully hear me? Okay, so I'll take that as a yes. Today I'm going to talk about supermassive black hole binaries and the search of these systems in time domain surveys and some of the challenges we have encountered so far and opportunities for LSST. So Ethan, of course, gave a very good introduction about why we expect these systems. I just want to repeat very briefly. We know that every massive galaxy has a supermassive black hole in the center, and we also know that galaxies merge very frequently in the history of the universe to build up the more massive galaxies we observe today. And we also know that in these galaxy mergers, typically we have a lot of gas that is involved in this process. And that gas can be very important for searching these binary systems because it can accrete to the black holes and produce the bright electromagnetic signatures that will allow us to find these systems. So we expect that these systems form frequently and they are surrounded by gas, so they may produce bright electromagnetic emission. And separations is to find quasars with periodic variability. So why can you hear me?
Yeah, we're kind of losing audio a little bit.
Can you hear me all right then?
No, yeah.
Okay. So why do we expect to find binaries in quasars? We know that at least some of the quasars are activated by galaxy mergers. So that makes them very good hosts for finding galaxies that have two supermassive black holes. Why do we expect periodic variability? Again, I would say this is fairly intuitive. We have a system that is periodically perturbing its environment, but this is something we have seen also in various hydrodynamical simulations. So when we put two black holes in a gaseous disk, the binary will expel the gas from the central region, producing a low-density cavity in the center, but there's a lot of dynamic interactions between the gas I'm sorry about that, and the edge of the circumbinary disk. So, for example, we have these streams that periodically enter the cavity and accrete onto the black hole. So if we look at the accretion rate onto the black holes, we see periodic modulations. We also have these mini disks that can travel with relativistic velocities. And for example, if we have a relatively unequal mass binary with an inclination which is not too far from edge on, when the smaller black hole moves towards the observer, its mini disk will appear brighter. When it's moving away, it will appear dimmer. And that gives rise to a very smooth sinusoidal periodicity. So now in the last 10 years or so, we had a lot of developments in the search for quasar periodicity and therefore the search for binaries, because we had large samples of quasars in the time domain surveys that we had available that allowed us for the first time to search systematically for quasar periodicity. And of course, we will have LSST data in the very near future that will give even more opportunities to search for these type of systems. Now, searching for quasar periodicity has proven quite challenging, and we are at the era that we have a lot of candidates, but we don't have confidence that we have any real system. We're not in a position to confirm any of these candidates yet. So these are just some examples from the various photometric searches for quasar periodicity that have been done over the years, including my work with the PTF sample. But the emphasis here is on the word candidates, because as I said, it's very challenging to find these systems. And I'll just very briefly go through the challenges. So one of the reasons this is very hard is because we typically have very short baselines compared to the periods that we're looking for. These systems have periods of a few years, so it's very hard to observe many cycles of periodicity in the data. So this is just an example from the search in the ZTF data, a really large sample of AGN analyzed in this. And initially, looking only at the ZTF data, we had over 100 candidates. But then when these authors looked at historical data, it turned out that the periodicity was not consistent over many cycles. So out of these 100 and something candidates, only just 3 survived, which, as Ethan said, maybe they don't even survive with the other analysis we have done. The other major limitation is that quasars have stochastic variability, which can mimic this periodicity, especially when we don't see many repetitions of the periodicity. So with Jakob Robnik, who is a graduate student at Berkeley, we developed this new method to assess the significance of periodicity. So we use null signal templates. So practically, we take a periodic template and perturb it to make it oscillatory but non-periodic. And then we apply that to the data. So whatever is picked up by this template is by default a false positive. So we can assess what is the distribution of our test statistic without making any assumption of the noise. And we applied this test statistic in the PTF data. And what I'm showing here is the distribution of the base factors using the periodic profile template, the null signal template, and also applying this template in simulations of the dumb random walk. So what we find is that the tail of the null signal template gives higher log base factors than the periodic template, which means that none of the candidates we had identified in PTF remains statistically significant. The other thing is that the dumb random walk cannot reproduce what we observe in the real data, which shows the limitations of this model. A final limitation is that so far we have only looked for sinusoidal variability. We expect this to happen in a part of the parameter space, but very often we also expect significant deviations from this sinusoidal periodicity. So with Meng Lig, who is an undergrad at Columbia, we looked at how many binaries we would detect using the Lomskargol periodogram as our search method. And it turns out that if we looked, for example, for sawtooth periodicity, which is what the hydro simulations predict, we would miss many of those. So Here is the recovery rate as a function of the parameters, for example, the signal to noise ratio, the amplitude of the periodic signal, or the period. So we see that when we have very strong signals, we can recover most of them. That's not the case when we look at sawtooth periodicity. And also, it's much easier to find the short period binaries rather than the longer period binaries, which of course is a big problem because we expect many more binaries to have longer periods. Now, to address this limitation, with my graduate student Indian Davis, we started building a very big catalog of binary templates and trying to simulate how exactly they will look in LSST. So we're doing this on behalf of the variability subgroup of LSST, and we're producing periodic templates using both analytical models and hydrodynamical simulations. We inject realistic noise, which is, it will vary between the dumb random walk, the dumb harmonic oscillator, and some higher order karma models. And then we also use realistic observing cadence from LSST, both for the wide fast deep and the deep drilling fields. So eventually we will have about 2 million periodic templates to train our algorithms to find these non-trivial periodicity that the Lom's-Cargill periodogram has a hard time to find. So the final thing that I want to say is that so far I have focused only on the periodic variability, but there's a whole array of signatures that the binary can produce. And since we're having such a hard time to find binaries with just quasar periodicity, maybe we will need to look for convergence of evidence in the end. So in this review, we have compiled all the potential signatures that one can look to find these binaries. For example, if there's a jet associated with the binary, as the binary moves around, the jet will be distorted. If there's a broad line region, there will be Doppler shifts. We may be able to observe gravitational waves. Now, the problem with each individual signature is that none of them is unique. So it's very easy to confuse them with typical AGN behavior. And the final thing that I want to mention is that as part of this review, we have put together a list of binary candidates that have been reported in the literature. And we have this spreadsheet that we are trying to keep up to date. And you can find the candidates here. And of course, we're happy to receive any feedback about this database that we are trying to maintain. So thank you so much. And if you have any questions, I'm happy to take them now, or you can reach out by email.
Any questions? I guess I could ask a question. Could you maybe, I think you mentioned something about how, current tools are not able to measure the type of periodicity that you expect. Like, could you say something about like what tools would be better suited, or like is someone working on the types of tools that you need?
Yeah, so there's a few things that I've been thinking and my group has been thinking. One is that you could use mass filtering. So we have templates from analytical models or hydrodynamical simulations. You could try to apply those, modify, instead of using a periodogram, which has a template which is sinusoidal, you can use a different template. The other possibility is to use something like machine learning or neural networks. As far as I know, this has not been tried in the search for quasar periodicities. So these are the tools that I have in mind. There's probably more. I know in the stellar periodicity case, they do have atypical periodicities. The periodicity there is not always sinusoidal, so we could probably borrow tools from there.
All right. Well, thank you so much. Next, we have the last scheduled talk of the session from Igor Benatti-Cohen-Salvins, who will be talking about exploring quasar variability with ZTF at redshift between 0 and 3. a universal relation with Eddington ratio.
Thank you. Can you hear me, Yuval? Yes,
I can hear you, and your screen is not full screen yet, but you are sharing.
it's kind of low. Okay, I can see. So thank you everyone for the opportunity. My name is Igor, as we may already read there. I'm recently completing my master's degree at the Federal University of Rio Grande do Sul, and we're now looking for PhD positions, of course. And today I'll be talking about really quickly about this paper that was recently published. I think last month. Yeah, last month we got accepted and published at the Statistical Journal, and it was basically the work that we did during my master's with Panda, Thaisa, and all of those co-authors. And the idea here was to explore the quasar photometric variability of quasars using ZTF and with AGN properties like black hole mass, luminosity, and so on. And we find this interesting correlation with Eddington ratio. Here is the sample, just talking about what we use it. We use it as subsample of the all quasar multi-epoch spectroscopy program, the ACMIS, which is part of the SDSS5 Black Hole Mapper project. And the original sample has more than 2,000 type 1 quasars, which spans a redshift range from 0 to 3. And we also selected only the declinations below 30 degrees to use the same sample on the LSST in the future. And here's the sky distribution showing in red the ACMIS median, the sample that we use. As for the data, as you already noticed, we use the ZTF, the Zwick Transient Facility. We use it specifically the forced photometry of the ZTF. I'm not going into details right here, but basically it's working since 2018. And we have these 3 bands available, G, R, and I, with a reasonable cadence that is really interesting, but we hope to improve this cadence with the LSST, as well as the filters. And well, okay, just to give a glance on the ZTF filtering, we have here 3 SDSS spectra from our sample with different redshifts, as you can see. They have different emission line contributions. Here is just to show that there is some emission lines that may contribute, that seems to contribute a lot in the different filters. We managed to calculate how much of the emission lines were contributing to the filter and in respect to the continuum, and just to make sure that the variability we were seeing on these light curves were driven by the continuum. So, and we find that yes, this variability is mostly from the continuum, even regardless the redshift we are looking at. Okay, this is the filter light curve. After all the process to achieve this light curve, we needed to construct this Python custom code that is open accessible through this GitHub link. There are some examples that you can play with of light curves, but I'm not going to details right here again because I don't have much time. But basically, it removes the non-values, it removes the outliers, and also the light curves that don't have more than 100 observations per light curve. And also, the important thing, we defined this F bar as our variability parameter, which is also known as the excess variance, or I don't know, the F bar, basically. And once we have the light curve filtered, and you can apply the F bar, and you can obtain the light curve variability. And here is what we did. Here I'm showing the G and R histograms for the F bar, divided into 5 redshift bins because as I showed, there is a broad range of redshift, and we wanted to make sure that we are not biasing that much our analysis. And also here you can see that the G band has a slightly higher number of sources, and also a higher variability in all redshift bins. And that's why we choose the G band as reference. So from now on, we are going to use the G band as the variability. And well, we have the photometric variability. We just need to obtain the features of the AGN, right? And for that, we performed this cross match with the Yu-Shan 2022 quasar catalog, and obtained a lot of information like the bolometric luminosity, the black hole mass, the Eddington ratio, and so on. And right now, just I need to put the things together to look for correlations with those properties. And that's what we did. Here I'm trying to just to show the black hole mass against the FVAR, both in log, just showing that also we performed the Pearson coefficient correlation, also the p-value with the new hypothesis that there is no correlation between those two. And we find some interesting results on the black hole mass. On the luminosity, there's nothing new. There is a persistency negative correlation. And what is most interesting, because I wanted to skip this just to talk about this relation, I think is the most interesting one. We find a a negative correlation between the Eddington ratio and the FVAR, the photometric variability. This persistence correlation is across all redshift beams, although the last redshift we have this outlier here. But once you plot the all points, the overall regression, and also see how the points rely on near this overall regression, you kind of see that the data relies really well near this relation. Here I'm removing the redshift beams regression to show just the overall regression and give it more to show it better, just like that. Also, the CI, the credential interval, and the prediction interval are shown here. The main result is that we find there's persistent anti-correlation between those two parameters that appears to be universal in all redshift beams. And we derived this linear regression that basically, in log space, of course, that basically tell us if you have the photometric variability of the source, let's say in a 1 year light curve or more, we are still working on that parameter, time parameter. You will have the Eddington ratio, and of course you also have the black hole mass. Since you have the bolometric luminosity, you can achieve the black hole mass of that source. So that's an interesting way to use the photometric variability to obtain a notion of the black hole mass that we are looking at. And I think I'm almost off time, but I'm gonna let the conclusions right here, and I'm glad to take any question. Thank you.